Now let's see how the determinant corresponds to the volume change factor for a linear operator. So this is theorem 10.52. If T is a linear operator on Rn, actually is a positive operator, and omega is just some subset of Rn, then the volume of the image T of omega is equal to the determinant of T times the volume of omega. So omega changes by a factor of det T under the transformation. And so we do this first for a positive operator. So let's see. So for the proof, the first part of the proof, I'm actually going to repeat the proof of an important fact, which is part of a larger collection of results known as the Spectral Theorem. And the part that I'm interested in states that if T is self-adjoint, which is the case for a positive operator, then the eigenvectors for different eigenvalues are orthogonal. And so the way that it works is like this. If I take the jth eigenvalue lambda j, and I put the corresponding eigenvectors vj and vk into the inner product, then you can pull scalars in and out of the inner product. So I can push it in, and I have, this expression. And then since that's the eigendata for T, that's the same as T vj vk in the inner product. And then I can push this over to the other side. I can pull T over to the other side, and it comes with its adjoint on the other side. However, we're dealing with the self-adjoint operator, so I can remove the adjoint in this special case. So this is when T star is equal to T. I can do this step right here. And then I have Vj lambda k vk, and I can pull this scalar out in front as well. In general, when it comes out of the second slot, I have to worry about taking it out as the conjugate, but we've got a positive operator, so that means that I've got positive eigenvalues, and so in particular they're real eigenvalues, so it's actually going to be equal to its own conjugate. So it comes out as lambda k vj vk. Now from start to finish here, if I subtract the rightmost thing over to the left, then I have lambda j minus lambda k vj vk equals 0, because the terms on the leftmost and rightmost side are equal, right? And so then if those are distinct eigenvalues, then that means that Vj and Vk are orthogonal. They have dot product or inner product 0. So that's the meaning of orthogonality. So there's my little symbol for Vj and Vk are orthogonal vectors. Okay, and then if you have a repeated eigenvalue, it also turns out that you have you get a full basis of eigenvectors, and so then you can choose the eigenvectors for that subspace to be orthogonal to each other. Just like if you know you have a plane that's invariant under T, then you can pick any orthogonal basis for that plane that you like. Okay, so based on all this, we can choose an orthonormal even, by choosing them all to have length 1. You can always normalize a basis. We can choose an orthogonal, or orthogonormal. That's not actually a word. What the heck did I do? Okay, orthonormal. Okay, so they're mutually orthogonal and they all have length 1. Basis of eigenvectors. And we use these coordinates to define our boxes. Okay, so now lambda k is the scaling factor of our transform. So it's also the factor by which t scales the kth side length of a box. Right? And so what we see is that the volume of t times a box is the product k equals 1 to n, and now lambda k scales rk. So we have this, but the product can be written in whatever order we like. So we can pull all the the lambdas out front and then have all the radii like so, and then that's just, well, the first part is the determinant of t and the second part is the volume of the original box B before applying the transformation. Okay, so we've now proven that the purported volume factor change formula holds in the special case of a box, but then it extends by linearity through summation and infimum. So by that I mean taking sums of boxes. This is a linear operation. So in other words, if you take the sum of axn plus byn, where n is your index of summation, this is the same as a times the sum of the xn plus b times the sum of the yn. So summation is linear. And infimum is positive linear. By which I mean that the infimum of ax plus by is equal to a times the infimum of x plus b times the infimum of y, as long as you're taking the infimum over the same set. And then this is crucially for when a and b are non-negative here. But that's going to pose no problem for us because we're looking at volumes of boxes, and these volumes are always defined to be positive, so there'll be no problem there. So this carries over to volumes for arbitrary sets. Okay, so now so that's what so we just got that last result for positive operators. Now we'll do it for isometries, and then in the end we'll do it for arbitrary linear operators. So if S is an isometry, then the volume of the image of omega under S is equal to the volume of omega. And so the proof of this is basically just a restatement of, hey, S is an isometry. So for x and y in Rn, the distance between any 2 points x and y after the transformation, well, by linearity, we can rewrite this as s times x minus y. And then because it's an isometry, this is just going to be x minus y. So this is just saying that the distance between points after applying the transformation is equal to the original distance between the points. So no side lengths change. And so in particular, the side lengths of a box B is unchanged. And then once again, this carries over to looking at the volume of omega under the image. Okay, and so for our last trick, we combine these. Because the last two theorems have given us the two parts of the polar decomposition that we need. So now for any linear operator, oh, and I'm saying V, and I just realized I shouldn't have been doing that. Where this is all taking place in Rn, where we're talking about volume and geometry of the determinant. Sorry about that. Yeah, so let me just, like, that was back here. This was Rn as well. Okay, so for any linear operator on Rn, the volume of the image of omega under T is the determinant of T times the volume of the original set before the transformation. And with the tools that we have in hand now, it's pretty straightforward. The volume of T of omega is the volume of S square root T star T applied to omega. And then this is, well, that's S applied to something, so that doesn't change the volume at all. So this is the volume of root T star T applied to omega, and that's by 10.53, the previous one we just did. And then this is going to be the absolute value of determinant T times volume of omega by our result earlier for positive operators. So this is 10.47. And we are done. And at this point, I just realized I misstated the actual statement here, that this should have been the absolute value of the determinant. Sorry about that.